Hi, this is Mrs. Mays. We're going to work through equilibrium calculations. This is part 4. You may have already seen the first 3 parts, but in this one we're going to use the small x assumption when the k value is very large. There's some special techniques we use here, so pay attention. First, let's look at our reaction. Hydrogen plus iodine makes hydrogen iodide. And these are gas phase reactions. We're given a K at 25 degrees Celsius, and we're given grams and liters. So we have to do a little bit of extra work here. First of all, let me see what I have. We're going to have to turn grams to moles. So I have 15.9 grams of hydrogen gas, and I want to turn it into a molar concentration. So I'm going to go ahead and go from grams to moles. 1 mole of hydrogen gas, H2, is diatomic, weighs 2.02 grams, and I need moles over liters, so I need my 5 liters to go on the bottom. And that gives me, let's see, 1.56 molar hydrogen gas concentration. For iodine gas, I have 294 grams of iodine, which sounds like an awful lot, but iodine is quite a heavy gas in terms of its molar mass. So I'm going to go ahead and work this out. 1 mole of iodine weighs 253.8 grams. That's a big molecule, and that's in a 5-liter container, so the molar concentration of iodine is 0.232 molar iodine gas. And here we had a decimal in there that didn't show up. Okay, so I know my molarity, and look how small the amount of iodine is. Since I have a 1-to-1 mole ratio, I know that the iodine is going to be my limiting reagent. Iodine is certainly going to run out before all the hydrogen gets used up. So I'm going to use that in my rice table. There's a few other things I want to consider as I approach this problem. First of all, I know that Q is going to be equal to 0 because I don't have any product yet, and Q is less than K, which means more product will be formed than what I started with. We assume that when K is so very large, this one is 10 to the second, that's in the hundreds, right? Then the reaction is said to go all the way to completion. That means we form product and we don't have any reactant left that's measurable, really. So stoichiometry tells us that iodine is our limiting reagent. We're going to let it be the smallest when it's at equilibrium, because we say the iodine completely runs out, so we're going to assign the equilibrium value of iodine to be x, because that's the smallest that x can be. So let's set up our rice table and find out the initial, final, and changes in all of our concentrations. So let's start out by writing the reaction like we always do. Hydrogen plus iodine, and then our arrows, so we don't need this column, makes 2 HIs. And I said I want to put my X in my equilibrium spot for iodine because that one runs out first. The molar concentrations we calculated before were 1.56 moles per liter for hydrogen and 0.232 moles per liter for iodine. And we'll start with 0 product. Now, here's where the tricky part comes in. I want to remind you that equilibrium values come from adding initial plus change. So my initial is 0.232, and I have some change that I'm trying to figure out. My equilibrium value we're calling x. So I have to figure out what to put in the change column for my iodine. So I have to subtract 0.232 from both sides to move that over and get the change by itself. So I get a change in iodine of X minus 0.232, because our equilibrium always works out to be initial plus change. Now we'll use stoichiometry for all of the rest. If I have a 1-to-1 mole ratio for hydrogen to iodine, then the change in hydrogen is also X minus 0.232. That was easy. Now I have to double it though when I come to the other side, and I have to change the sign. So I take negative 2x plus, because minus a negative makes it a plus, and then I double 2.32 and get 0.464. Did I say 2.32? Yeah, you meant what I knew. Move the decimal in front of the 4. You're okay. All right, now let's calculate equilibrium values for everything else. So add initial plus change. We're going to combine like terms here. So I get X plus 1.328 because I've combined the 1.56 and a negative 2.32. And for HI, that's easy because I'm just going to call this negative 2x plus 0.464. Easy enough, right? Because 0 plus something is still that thing. Now what do? Remember, once we get our chart filled out, we start putting things into our equilibrium constant expression. So let's write that first with variables. Hydrogen iodide goes on top, that gets squared. Hydrogen gas times iodine gas goes at the bottom. And that is equal to 7.1 times 10 to the second. When I put my equilibrium values in from my Rice table, what do we get? Okay, HI goes on top. I'm going to write this backwards so that you see where my adding and subtracting of X comes in, because this is the same math. I just wrote my constant first before the variable, and that one gets squared. And then at the bottom I have 1.328 minus, no, plus X, right? Yeah, plus X, and iodine is just X. Okay, now with this small x assumption, we can get rid of any x that is added or subtracted in our expression. Any x that is being added or subtracted. Not anything that's multiplied or squared or any of that. Just added or subtracted. So what are we looking for? First, this one. If x is really tiny like we want it to be, then that means, oh, I shouldn't have x'd it out. That means that this just basically is so small that it's not going to have any impact whatsoever in my number. The 0.464 minus some teeny tiny thing, even when we double it, is still equal to 0.464 because we don't get to keep all the sig figs at the end anyway. And the same is true for this x in the denominator that's being added. That's just going to not even make any difference whatsoever. X is so minuscule that it doesn't even matter. So that's my small x assumption. Now I've gotten rid of all of these other things. That's going to make my math easier. Look how I can simplify this algebra. So I get 7.1 times 10 to the second is equal to 0.464 squared divided by 1.328 times x. How do we solve for x? Well, we use algebra. Manipulate your equation, rearrange things, and I ended up getting x equals 2.8 times 10 to the minus 4. So go back and check math, but what we find is that indeed the value of x is so small that it's like 4 decimal places in, and we don't have that many decimal places to be able to measure. Such a tiny amount that it's not going to change the values we've been working with. So we're not done yet. Let's answer the question that was asked. We need to calculate the equilibrium concentrations of all of our substances. And what else do we need to do? That's all. Equilibrium concentrations of every substance in the container. So, here's what I know. I know that the concentration of iodine is equal to X at equilibrium because that was our starting place from the very get-go. So the concentration of iodine is 2.8 times 10 to the minus 4 molar. The concentration of hydrogen is going to be X plus 1.328, and that's going to work out to 1.328 because adding 2.8 times 10 to the minus 4 plus 1.328 is still 1.328. Doesn't change. And then the concentration of hydrogen iodide is going to be equal to 0.464. Oops, that decimal ended up in a wacky place. 0.464. Start again. 0.464 minus 2 times X. And when I do all the math and put it through the calculator, I still only get to keep 3 sig figs, so I get 0.464 molar. In fact, how many sig figs did we start with in our mass? Oh darn, I turned the page. 1, 2, 3, 1, 2, 3. So this has too many sig figs. I'm going to call that 0.33 molar. 1.33 molar. That's 1.33 molar. And that's 2.8 times 10 to the minus 4 and 0.464 molar. Great. We now have the concentration of everything that was in our reactant vessel. So the rule of thumb is that if the value of X is less than 5% of all the other concentrations, then our assumption was valid. If the value of X is greater than 5% of any other concentrations, then we would have to use the quadratic equation, and this method wouldn't work. Quadratic equation. So when you use the solver, let your reader know that you're using the solver. If you use the small x assumption, then make sure that your reader knows you're using the small x assumption so that we can follow your logic in your equilibrium problem. But that's how we would handle a problem where the value of k is very, very large. Let me show you another technique in another podcast. Thanks for working through the problems with me, and I'll see you soon.